This video is on graph representations. It's the second video in a basic graph algorithm playlist after the introduction to graphs. This one goes over the two most common ways to implement graphs, adjacency matrices and lists. After a few simple representation-related algorithms, I'll compare their strengths and weaknesses. So you have this abstract graph out there with vertices and edges, and maybe each of those has information that goes with it. The graph representation we choose is just some implementation which captures that abstract graph information. But you can come up with different implementations to capture the same graph. The two most common models are the adjacency matrix and the adjacency list. Starting with an adjacency matrix for a directed graph, we use a two-dimensional matrix. We assume that vertices are numbered and an edge from vertex I to j goes in row I, column j. What do we store for the edge? In the simplest case, just a single bit, true or false, if the edge exists. In the most complex case, you can store an edge object or maybe a reference to an edge, where that edge can store whatever information you want, weight, name, hobbies, whatever you need for your problem. A common case between those two extremes is when you just need an edge weight. So great, just store the edge weight in the matrix. But what do you store if there's no edge? Some languages might allow you to store nil or a null reference, but even then, each time you need an edge weight, you first need to see if the edge exists and then use it. That slows your code down a bit and also makes it clunky. Instead, depending on what the weights represent, it's common to store a dummy weight for missing edges. If weights represent something you're trying to minimize, like a cost, you store a huge value, like infinity. If you're minimizing cost, you should never take an infinite weight edge unless you can't solve the problem without one. Again, depending on what the weights represent, other dummy weights for non-existent edges might make sense. Hugely negative, 0, or hugely positive are the most common values, where negative infinity might be used if edge weights are profits that you're trying to maximize. Finally, for undirected graphs, the matrix is symmetric over the diagonal, so you could try to halve your space by just keeping one side. The Corman book mentions keeping the top part, but I think the indices come out cleaner with the bottom part. Next comes the adjacency list representation. Here, we have an array of vertices, and for each, you have a list of its edges. In the simplest case, if your current vertex I has an edge to j, maybe you only need to store that index j in i's list to mark that the edge exists. You can't get away with just a single true-false bit here. You have to identify the other vertex. For a weighted graph, you can't just store weights. You also need an index or reference. What do you use for lists? You can use any list, and if the graphs don't change, you can even just use static arrays. If the graph never changes, and you frequently have to look up whether or not edges exist, you could even use sorted arrays and then just use binary search if you're looking for a particular vertex in a list. If you care about quick lookup and also want to let edges be added or removed, you could even use a balanced binary tree structure. But for lots of algorithms, you only look at all edges incident on a vertex in arbitrary order. There, pretty much anything you use is fine. I'll just show comma-separated text in my slides. For undirected graphs, in the adjacency list model, you store each edge twice, once in the list for each vertex, unless you don't care how long it takes you to look anything up. For directed graphs, you have a choice. For each vertex, you can store all of the vertices that it has an edge to, or all the vertices that it has an edge from. Those are two different ways of storing the same graph, and you pick one depending on how you're going to need to access your data. Storing outgoing edges is more common. For some problems, you might want both lists. What if you're given the data as an outgoing adjacency list, but you want the incoming list? You can go from one format to the other in time linear in the size of the graph. Given an outgoing representation, you create a new incoming representation with the same vertices, and then for each vertex I in the graph, for each vertex j in i's outgoing list, append I to j's incoming list. Let's quickly run through an example. If vertex 1 has a link to 3, append 1 to 3's incoming list. If 1 has a link to 5, append 1 to 5's list. And if 2 has a link to 4, append 2 to 4's list. Do that over all edges. It takes constant time per edge plus constant time per vertex. Done. Going from the incoming list to the outgoing list is the same algorithm. Going from an adjacency list to a matrix is very similar. Make an empty matrix, or for a weighted graph, a matrix filled with dummy values. Then for each vertex, for each outgoing edge, add that edge to the matrix. It takes time no more than the size of the matrix, the number of vertices squared. To go from the matrix to the outgoing list format, create an empty list, step through every location in the matrix, and when there's an edge, add it to the appropriate list. It takes time proportional to the number of vertices squared to look through the matrix. One final graph manipulation algorithm. Flipping the direction of each edge in a graph is called taking the graph's transpose. Because if you're using the adjacency matrix format, you just take the transpose of the matrix. If you're using the outgoing adjacency list format, just find the incoming adjacency list for the same graph and interpret that incoming list as the outgoing list. That's the transpose. So great, we have multiple representations for the same graph, which can transform one into the other as needed. Assume you have whichever representation suits your needs most. Let's compare the outgoing list to the matrix to get an idea of when to use each. First, let's look at the space or memory usage. The adjacency list has one list for each vertex, and each edge shows up in one of the lists, or two for undirected graphs. That's space linear in the size of the graph. The adjacency matrix takes up size quadratic in the number of vertices. Is that bad? Depends on how dense the graph is. If the graph has enough edges, the matrix could actually use up somewhat less space than the adjacency list, but for sparse graphs, the adjacency list is asymptotically better. If we think about Facebook, each user has, on average, a couple hundred friends. It's a lot easier to store 100 links per user than to store a billion by billion matrix for the graph as a whole. What tasks does each representation do well? The most common basic graph operations are to ask what vertices are adjacent to a vertex and to ask if an edge between two vertices exists. Iterating through a list of vertices adjacent to a vertex is easy with an outgoing adjacency list. It takes time linear in the size of the list, which is the vertex's out degree. The matrix format takes time linear in the total number of vertices in the graph. Again, not bad if the graph is dense and the vertex has an edge to most other vertices, but it gets worse and worse the more sparse the graph is. Again, for Facebook, imagine how wasteful it'd be if they had to run through over 1 billion users just to see what they should stick on your friggin' feed. No one's that popular. The matrix can find out if some edge exists in constant time, while the list might take time linear in the degree of one of the edge vertices to run a linear search. If you expect to do lots of those lookups and decide to have the list sorted in arrays or trees, each lookup will only take time logarithmic in the degree of the vertex, which might be small compared to the number of vertices. That might be worth doing sometimes, but for lots of nice algorithms, we don't look up whether or not an edge exists. We only want to list vertices by adjacency. Even though we'll occasionally use the adjacency matrix, the adjacency list is our default, including for the videos up next on this playlist, breadth first search and depth first search. For now, I've got to go practice my miming skills.